All right, I'm so loud, but I'll do it because I know they're on Zoom. I'm sorry if I hurt people's ears. You can keep talking. All right. Is it working, Johnny? Do we know? We should ask the people online. If you guys can hear me, will someone say on chat in the Zoom that they hear? Great, fabulous. Hi, guys. Welcome to Austin, where it's not as hot maybe as Louisiana. I don't know, but it's going to be a hot day. So hopefully you have a hat. Congratulations for finding this room. You are not in the physics department, though. I guess I should tell you I'm Deirdre Shoemaker. I'm here at the Center for Gravitational Physics. So PMA is the physics building. It is behind us or somewhere. If we walk out, it's like right up there, the really tall building. If you wanted to visit for some unknown reason, the Center for Gravitational Physics, we're actually in a different building, a few buildings down. So it's really hard to find us. We're kind of hidden. You'd probably need one of the locals to take you. But I have not decorated the center, so don't visit. It doesn't look good. So Pablo Laguna wanted to be here to greet you today, but our dog had a surgery on Friday, so one of us has to be home at all times. I'm going to disappear because I don't trust him to take care of my dog, which is terrible. But true. It's a true story. So I'm so sorry because I won't hang out with you. I'll be on Zoom. And if you need anything, tell Johnny and he'll contact either Pablo or I to help. But I'm just one of those, I don't know what I would do if I had a human baby. The dog baby's enough to kill me and make me watch her at all times. So let's see what else you might need to know. You already know the coffee's outside. The women's restroom is you take a right as you come out this door. The men's restroom is you take a left. I don't know if there's a gender neutral in this building. I don't know if I've seen one. We have one in our building. I don't know if there is one here. Let's see, what else do we need to know? Lunch is not catered or anything, so you have a lot of options. I don't know if the locals are going to be going to lunch, but the closest is on the road behind us. There's like a taco joint and a couple, burger fry beer places called Crown and Anchor and Posse East. And the taco joint is literally called Taco Joint, so that makes it really easy to remember. There's a lot more options if you want to walk up to Guadalupe, but it's a little bit far. There are some really local options, like right behind us in the buildings. There's those cafes that are associated with universities. They're not bad. There's one very close if you really didn't want to walk much. What else does anyone need to know? I guess that's everything. Okay, so we have a lot of time for these talks, so I've been trying to delay. Okay, so I can't talk for now. Yes, Johnny. Yeah. That's going to take a second.
I don't want to say anything.
All right. You didn't believe me. You're going to have to give me the link. Oh, no, I haven't. Everyone can watch my email. Oh, don't look at what I haven't done. Oh, wait, I don't want that. I want ETK. You're trying to save me because you're like, she's going to get in trouble. Did they say they couldn't see the screen?
No, I said that.
The release of the new ETK toolkit is beating out the workshop for presence on the web. That's just slow. That one, gotcha. All right, we're joining. But I won't do any audio.
Yeah.
Yeah, I will. This is great. Can you just hang out with me all day? Oh, you have to let me. Who's host? Just kidding. Entertaining.
Great.
Yeah, you can do the whole screen. That'll be fine. Start. Yeah. I don't have any. One time I was giving a talk and Papa was messaging me and it was like, oh, shut that. It was very funny though. Who knows what that was going to be like. Thanks, Jenny. All right, so they can see it better, or you can see it better over there on Zoom? Okay, so I don't do matter simulations because they're hard and messy. So I'm going to apologize if I'm going to focus on binary black holes because I feel like I'm not expert enough to talk about the neutron star stuff. There's many more people in this room who are more expert than I am. So I apologize because it really doesn't give you the full breadth of, I think, the role of numerical relativity and gravitational waves. Joseph is going to talk about the Einstein toolkit in particular, as is Steve. So I didn't talk about that either. I was trying to find things that maybe other people weren't talking about. So it's a very kind of general talk on numerical relativity's role in gravitational wave astronomy and some kind of ads for how we might participate, assuming all goes well with budgets in the US. Okay, so we're just going to pretend everything's fine today, okay? And we're not going to have an existential crisis while we're up here. So, okay. This is one of the movies Deborah made when she was a student or postdoc, I don't remember, of two black holes colliding. And that's going to be my focus. And on gravitational physics driven by data. So for the older ones of us, like what a revolution that is, that we'd actually be confronted with observations. For the younger people, this is what you're used to, which blows my mind personally, that you grew up in an era where, of course, binary black holes merged in the universe. And of course, we detect gravitational waves, but it was not our reality for a long time. So I think one of the biggest surprises was just how many black holes there are, because they're much more massive than people thought from stellar evolution studies and from detecting X-ray binaries, which has been great for people like me who study vacuum GR, because we see binary black holes all the time with gravitational waves. It hasn't been so great for multi-messenger astronomy because we are having a harder time detecting the binary neutron stars. No failing of the detectors. It's just maybe the event rates aren't as high as people had hoped. And also, even when you see the binary neutron star in gravitational waves, the hope is that you would also detect the electromagnetic emission, which we did see famously once, but not since then. So it's been a little bit trickier for that very exciting aspect of gravitational wave astronomy. So we are in that moment where actually the fourth observing run of LIGO and Virgo is about to start the last piece, I think, in July. Got delayed a little bit by a week. Maybe it's this week at some point we do the last run. So plans are in progress for the future of ground and space-based gravitational wave detectors. And as I sit here with a bunch of maybe younger graduate students, et cetera, I will say there is a huge role that numerical relativity plays in these detectors. So there's a lot of opportunities to engage as a theorist or as a data analysis in this exciting prospect of gravitational wave astronomy. And right now we provide really the means to predict and interpret. So it's important that we are out ahead of these detectors and really scanning the full parameter space of possibilities, because they're used to, especially with ground-based detectors, make the detection. And with both ground and space, they're going to be used to understand the sources. And as we get better and better with these detectors, they'll be used to test general relativity. Because really what's so fascinating is these gravitational waves provide that look into the strong field regime that nothing else can. So I think what we're trying to do is figure out what story the universe is telling us about gravity, if we can hear it. So these aren't all the science drivers. It's just a random list of science drivers, but just to get a feel for what we're hoping to get out of this as we move forward. We have learned a lot, right, already. And I'll talk about that in a second. But as we look to the future, because we're still in baby gravitational wave astronomy, right? It actually hasn't been around that long, especially when you think of optical astronomy. So the big ticket item is Einstein's theory, the correct theory of gravity? I mean, the hope is no, right? We're looking for hints that there's something else that we can learn. It might not come from gravitational waves, but we still have to push really hard. And I think this is one of the big ticket items for you guys in this room, because it's going to demand more and more from numerical relativity as a prediction of the gravitational waves from compact binaries, be it neutron stars or black holes. And that's not going to go away. It's not like we solve it once and we're done, because as the detectors get better and better, we have to get better and better, which I'll talk about later. So as these ground-based and space-based detectors open, we really open the range of black holes we can see from what we see today, which is like 10 solar masses, 100, sometimes 200, which is surprising, all the way out to 10 to the 9th if you get to PTA, 10 to the 9th solar masses. That is not really interesting for numerical relativists because they're really inspiraling, almost like Keplerian. It's not, so we don't need NR for the pulsar timing measurements of gravitational waves. But when we get to LISA and stuff like that, you're going to see 10 to the 6th, 10 to the 8th, maybe 10 to the 7th, solar mass black holes actually merge in band. So you will see that full merger, which is the hallmark of strong field gravity. Obviously, what would be super, super exciting is if we could get a high enough frequency detection in gravitational waves to actually see the merger of the neutron stars. Right now, we just see the light last in spiral, where you can hope to see tidal deformations of the neutron stars. But if you can get a little higher frequency, depending on the equation of state, you'd actually get a huge amount of physics, because you'd be looking at the nuclear physics, the equation of states, all this stuff that only neutron stars can tell you about. So that would be huge. To get to that place. Because of course, as we saw from, if you guys remember, from that first gravitational wave detection of a binary neutron star that was connected with a kilonova, we learned so much about gamma rays and gamma ray bursts, and where does platinum and gold come from? Fun stuff that you might not realize are associated with binary neutron star mergers, many things, and also tests of the speed of a potential graviton and things like that. So it's a wealth of physics information. As we move towards black holes themselves, as we can open up these new detectors, you'll see actually all black hole mergers if you have ground and space operating at a very high level at all masses. So we'd see the formation history of black holes and galaxies. And at some point, we should be able to probe the early universe, in the future, not now, and measure gravity near black holes, et cetera. So there's an awful lot to come. So the discovery potential is huge, but with that discovery potential always comes huge demands, not only on the experiment, but also on us, on being able to do the predictions, do the data analysis, et cetera. So there's a lot of fun stuff to do. Oops, I didn't care. I switched past that slide so fast. Why would I still care about vacuum? I remember when the first detection happened, not first detection, the first 2006, 2007 is ancient history. I know. After the first merger was done, everyone was like, "Oh, you're done. You got the solution. You can quit now." But it hasn't been true, has it? We're still busy. And so why should you still care about vacuum? It isn't as exciting, especially astrophysically, as the neutron stars. There's a wealth of things you can learn from neutron stars. Nonetheless, the biggest source of gravitational waves is and will continue to be black holes. And so we really still have to keep our drive in the vacuum in our case, because we're going to see all these black holes merging in the universe. We should, when we get to a strong enough detector, really be able to probe Einstein's equations as the solution to gravity. And there's a lot of open questions about gravity and black holes that as we get better and better, we're going to be able to dive in and learn more about strong field gravity. And there's potential to go beyond that, right? So if you're really interested in the fundamental physics aspect, there's fun things like, can you learn about dark matter and other ways to use gravitational wave detection to learn about fundamental physics? So the number one goal in my mind is to ensure the quality of gravitational wave science is not limited by our capability of solving Einstein's equations. Whether you do post-Newtonian, numerical relativity, or self-force, we don't want any errors we have to contaminate the data, because if you really want to, it's not going to be hard to figure out the mass of a 10 to the 6 solar mass black hole colliding with another. That's going to be so large in a space-based mission that you're going to see it without having precise numerical relativity. But if you want to be able to say whether or not GR is the true solution, we're going to have to be more clever than that as we go on. We're going to have to be quite good at our job. So this is really for anyone who's not a professor teaching GR, et cetera. So I apologize. But I love the PhD comic strip. Who doesn't? Have you guys seen it? It's so funny. If you haven't seen it, you got to go look it up. Very cute. Sometimes I feel sad because now I'm a professor and not a graduate student, and it always makes us look really bad. But anyway, it's still funny. I'm like, do I do that? So this is just an ad for why the binary black hole problem tends to be the biggest source, is the biggest source of gravitational waves. It's very simple, right? We're looking for non-uniform acceleration to detect gravitational waves from massive things. An in-spiral is a very good source, and it goes with by gravitational energy. And so the more massive, the more energy. So black holes are always going to win that game. The only problem, and we see them further away, so that's why we see so many more black holes than we do neutron stars. And this is just showing that if we danced around, we would make small, but they're existing gravitational waves. I bring this up to remind us that why LIGO was built. It wasn't crazy, even though at the time, I think the astronomy community thought it was crazy, because it took a lot of time to get that first detection. That was the second version of LIGO running. It wasn't the initial LIGO. But Arecibo, may it rest in peace. It's a little sad to have lost Arecibo. It was used for this famous Nobel work by Olson Taylor to see the decay, like the two pulsars were orbiting, or two neutron stars were orbiting. And even though they were very far apart in this moment, you could tell that their period was changing due to the loss of gravitational waves. So the existence of gravitational waves wasn't really necessarily in doubt. It's just that were we going to actually be able to detect them directly and be able to probe the sources? So this is what it looks like, as you all know. I just was at Virgo a week or two ago. I haven't actually been to LIGO in a long time, but I tend to hang out in Virgo all the time, which is confusing. I've never seen Kagra. It looks really cool. But Kagra is not quite ready. Kagra is a Japanese mission. It is about 10, 20 years behind LIGO. And it has some more advanced stuff like cryogenics. So I don't know. I can't remember if they're expected to join the 5th observing run, but they won't be sensitive enough. They'll join 04. They have been in 04, but they're not sensitive enough to really make a difference. Virgo is the one in Europe, and it is not as sensitive as LIGO because of some design decisions that they're going to have to fix. But they will. It's going to cost a lot of money. But nonetheless, the presence of that third detector is important to do sky location and things like that. So we really need all these detectors. This is really a collaboration in a true sense because the science really gets better and better as we populate the globe with detectors. This was the first detection, the baby picture of the binary black hole, GW 150914. So this is what it looks like when you clean up the data. And this is what it looks like when you put numerical relativity on top of it. So, you know, y'all have seen probably a binary black hole waveform before. It looks like two black holes merging. So it was a pretty fun time to be involved in this world. So us, what do we do? Right? There's a bunch of ways you can talk about solving Einstein's equations. If your two compact objects are kind of look more like point masses rather than a neutron star or black hole, that'd be the top part of this. I know we have pointers, but I never use them. I don't know. The top part of this picture. If you have very unequal black holes, that would be to the right of this picture. So post-Newtonian and Minkowskian tends to live up here when things, you can treat them like point masses, they're not moving too fast. Then self-force, small RAS ratio lives over here, sort of. When you have a very separate masses, so you can use a perturbation theory in this round. So both of these are using some appropriate approximation to solve Einstein's equations. And of course, we live down here where no approximations are valid. This might be an exaggeration, depending on the physical parameters of the source. If it was equal masses, non-spinning two black holes, we probably can touch all sides of this picture. So we'd cover the full space. As you add lots of spin, lots of eccentricity, that's when we start separating out our ability to cover everything, to have the complete known solution for any range. This has been interesting recently, very interesting. Very recent, like the last few years, the small mass ratio has been pushing towards agreeing with numerical relativity, not at the actual merger, but quite close. So stay tuned for more and more pushing this way. So hopefully by the time like we're 10 years from now, there won't be any white space left, right? And then of course, what's added to this is us solving the equations directly. It doesn't end there. Then we have models. So I'm not going to call these models. I'm going to call these like approaches to solve Einstein's equations. And then I'm going to call EOB and phenom and our surrogate and all these approaches models that take the information from all these solutions and create models of these compact in-spiral mergers for use with gravitational wave detection. So there's several stages, but we all rely on each other. So everybody has to do stuff. If you have questions, you can ask. Otherwise, I'll just keep going. So it's a super old slide with almost no citations. How lazy am I? So I don't even know if it's true anymore. Let's check it. So we famously, right, we're actually at the 20-year anniversary of the solution to Einstein's equations, the first merger in orbit from Pretorius. And I was embarrassed enough to be the person that gave that talk at the APS, so I'm old enough to give the historical perspective talk. Okay. So the whole point here is to solve the full nonlinear hyperbolic partial differential equations that are Einstein's equations. It's an initial value problem. It's tricky. We need supercomputers. It takes weeks to months on machines to do this right. And there's several NR codes, Einstein Toolkit being one of the biggest collaborations. Really, it's Einstein Toolkit and the SXX collaborations that are the two biggest. So thank goodness ETK exists, because it's really important to have at least, there's many codes I'll show you in a second, but really Einstein Toolkit is one of the biggest in the arena. Thankfully, I consider this all good news, because there's a lot of approaches to solve Einstein's equations, and it's important that the community try several and compare to each other. It shows how robust we are at solving these equations. So, there's the famous BSSM formulation, generalized harmonic, and other things like Z4, et cetera. There's different ways of handling the fact that there's a singularity if you have a black hole sitting there in your computer. And the result has been, I would call it robustness. Like, we can work with each other and prove we are solving the equations correctly. It has resulted in public catalogs. I'll list them with their citations later, and all sorts of things. So this picture is just from one of the really long SSX simulations. And this is what I call the M&M picture, just to say how many parameters we have to deal with. The spins, the mass ratios, any potential eccentricity, et cetera. So that's just like a summary. This slide is really old, 2006 when this paper came out, but I think it's important to us to remember where things get radiated. Like, why is the merger such an important part of this gravitational wave detection? And it's because if you plotted like the energy radiated of this waveform, if we were looking at this envelope as it came in, here, this is where, okay, let's see. Let's start with the apparent horizon. So a common apparent horizon forms here. We're not going to look at where the event horizon forms. The event horizon probably happened before this. It definitely didn't happen after. Before this, so you can see that you already have radiated 50% of your energy. So 50% of the energy is going to get radiated between this common apparent horizon forms and the merger, or like post-merger. So that's not much time. So an incredible amount of radiation happens very, very quickly when these two black holes merge. So this is why that merger, when it's sitting in the sweet spot of the detector, is so powerful in gravitational energy. And then you can see things like 50% of the angular momentum will also be radiated. Like, this is the regime of numerical relativity, right? And we own so much of the energy landscape of these sources, is what I'm trying to get at. This plot, it's fun because it's fun to see how fast these things are moving by the time they collide. So I just like that one because it's crazy. Crazy. I wouldn't want to be in the middle of that collision. Okay. Shazam still exists. I just want to say that. Probably none of you know it, but a couple. So, this is the typical way we describe data analysis, is that especially with these ground-based detectors are very, very noisy because of anything, tumbleweeds, whatever, earthquakes, the breeze, very noisy. So it's like trying to pick out one person's voice in a crowded, loud room. So Shazam is an app that you can use to figure out what song's playing. Okay, and it uses the same technique, match filtering. So you sit there, you have every song that's ever played or ever existed, and you compare it to that one on the radio, and it tells you which one it is. So that's what you do for gravitational wave detection. It's that simple, right? It's just hard because you have to have that prediction of every song. And so the problem with numerical relativity is we put discrete points down in the parameter space of known solutions. And that's not super convenient if you're doing gravitational wave data analysis. So people model it for that reason and others to put in more information from post-Newtonian and self-force, et cetera. So you get this smooth model that's fast, hopefully, to go around. So you build these huge template banks of songs or gravitational wave signals doing a couple steps. So this little cartoon isn't the best. VJ has the best one. We should all go steal VJ slides. Where you're just doing this comparison and you're looking at the correlation below, and when the correlation peaks, depending on a lot of other statistical information, that's your detection. So where does numerical relativity come in? We don't tend to go directly to the data, so it has happened in the past, but it's not normal to directly use numerical relativity waveforms in doing the detection, but the numerical relativity comes in building the model. And what surprises me to this day is every time you read a test of GR paper, the way we're determining the final mass and the spin of the black hole is through NR fits. So the initial data, the initial parameters of the two black holes are coming from the actual doing the full template bank correction, and then you use the parameters that come from there, the initial masses, the spins, et cetera, and then you go grab all those NR fit formulas from Luciano and from Carlos, and that's what you use to find the final mass and spin. So we're not good enough yet to detect the final mass and spin of the black hole independently of those initial. Does that make sense? I have more later, but I find that fascinating that we're still doing that. Worries me in some sense. So this is what we currently look like from the published catalog. The 04 catalog is coming out very, very soon, or the portion of the 04 that's complete. But this is 03. So it's legal to show. And this axis means nothing. So the horizontal axis is just there. The y-axis is important. It's the solar masses. So you can see this one doesn't have the X-ray binaries on it. This is just the gravitational wave detections. Orange are two neutron stars, or neutron stars. Blue is a black hole. If they're uncertain, it becomes blue or orange. It means we don't know if that is going to be a black hole or neutron star. And so what happens with each event is you get two mass detections, and then you get a third mass detection from this interpretation of what the final mass would be. And so our expectation before gravitational wave astronomy was born is that black holes were like 5, 10 solar masses, and no, they're very big. And so one of the big challenges is how do you create these as these stars evolve and become black holes. So that's where we are right now. There's more. There's like 100 more detections that aren't on this plot. So I kind of already said this, but I'm going to say it again. Oh, this is VJ's. I forgot. See, I told you this is really cool. Is it going to run? I don't know. Nope. I'm not that good. Sorry. Okay. Well, just someday you'll see that plot and you're going, oh, it is a good one. So these are the models up here. So there's two pictures of them. This is Phenom. Is this EOV? I don't know. Who knows? So this is what people are doing when we build connections between the numerical relativity part and like the post-Newtonian information. Maybe this is NR, maybe this is coming from perturbation theory. EOB is different. EOB uses some more physics to create it. They use effective one body, so they're pulling in information in addition to the numerical relativity and post-Newtonian. So this is kind of a redundant slide because I didn't realize I put in two of them, but at least this one has some citations on it. Very early citations of the Phenom and EOB. And our surrogate right now is Vijay Varma is probably the lead on that. I would say are the best model waveforms if you wanted to grab one set to work with. The EOB waveforms are great, but they're slow to create because you have to solve an ODE when you use them. So I think the NR surrogate is probably the go-to model. So this is what I was babbling about a second ago, that one of the fascinating things about solving these Einstein's equations is that we go from a large parameter space down to a final mass and spin of a black hole, and maybe, and a kick, a gravitational kick, but I'll ignore that for now. So, we have an array of masses radiated and angular momentum that's radiated to produce that final black hole. And this is what I had said earlier, but now with some citations, et cetera, that what's happened is early on in the numerical relativity land, people used a plethora of numerical relativity solutions to start to say, given initial parameters of the black holes, you can predict what the final mass and spin are with some error bars. And that's actually what's used to figure out whether these black holes we're seeing with gravitational waves are Einsteinian or not. And so these lines are, we don't know when ring down starts. So ring down is the colloquial term for the state between I have formed a single horizon and I now have a single curved black hole. And this process of shedding the information is called ring down. And this is the no-hair theorem it's related to. We're going to ignore charge because we expect the black holes to be neutral in the universe. So he only has 2 hairs. Sorry, Homer. And what we don't know is the start of when ring down happens. So these are all different choices of when people are saying we've entered the linear ring down regime. And what you do is you learn the parameters from traditional match filtering of the in spiral of the signal. So you pick this part of the signal to know the masses and the spins, and then use these NR fits to calculate the final mass and spin, and then you check the data and see if it's consistent. So that's what's happening as you look at tests of GR right now. Someday, and they do use templates that are just built from perturbation theory, but because ring down is exponentially decaying and the noise is here, and this is a beautiful signal, it's really hard to see that last gasp of the merger. This is a pet thing, and I'm not actually working on it, but I like the work on it, so I don't know why I haven't asked a student to do this, but I think one of the interesting things that's going to come out of numerical relativity in the next few years is to really nail down. I don't think we really nailed down how nonlinear is the merger yet. I think it's not very nonlinear is what we're learning, but I don't think we've actually finalized that statement. And so back to the same plot we were talking about earlier, a lot of people have tried to work on this, and this is the newest bit of work, is that you kind of could have had this expectation that there could be crazy, interesting things happening as these 2 black holes collide. Could we be non-Kerr-like in that distorted black hole stage? Would we? No, what we do instead is the system radiates angular momentum like crazy. So by the time you form that distorted black hole, it does look Kerr-like. So we don't get these crazy regimes we might have hoped to get. So the question, and also when people start measuring for quasi-normal ringing, which should be in the perturbation phase, it matches much closer to the peak of the signal than you might have naively expected. So there's evidence that maybe what's happening is somehow as these black holes collide, they really form a Kerr-like potential very early on. And so things become, perturbation theory early. And so the latest thing, as I mentioned earlier, was that there's work showing that even self-force is starting to agree with numerical relativity. That's what this is. Self-force approximations, depending on the number of orbits, agreeing with numerical relativity earlier and earlier. At mass ratios you would not expect, like 1, where you would think the self-force is useless, and instead it's able to compare to numerical relativity reasonably well. So these are the hints that maybe things are really quite boring, and despite the challenge of solving these equations, they might not be that nonlinear. This depends on the physical parameters and has nothing to do with neutron stars. So it's only been done with the black holes, as far as I know. So what have we learned? We have learned, as I said earlier, that black holes are big. Are they spinning? Yes, but the earliest detections we made were very consistent with almost non-spinning black holes, which was a bit of a surprise. Now we're seeing more and more spinning black holes. Everything's been consistent with Einstein's theory so far. We're still babies, right? But there's no smoking gun of violations of Einstein's equations. And I already talked about all this. So it's and this is a better plot of like what does ring down look like if you had no noise in the signal. This is just from studying perturbation theory, and that's that beautiful exponential decay, which sounds really great until you have noise. And then it's really hard to catch that part of the signal. This is the challenge of detections even today as we speak. So for the first few years, the models might as well have been perfect. NR, 0 error, who cared? And because we were seeing a parameter space that looked like equal mass non-spinning black holes, right? And now more and more detections are coming out with higher mass ratios, some higher spins, precessing spins. Could they be eccentric? And what's happened is, as the detectors get better, we're more sensitive to a broader range of parameters, and you start to see the errors in the models. So now, if you start looking at papers, the models don't always agree with each other. So phenomena EOB-NR might give you different answers to the same event. And this wasn't true in early days of gravitational wave astronomy. So you could predict this would happen, right? As you get better, all your errors that you swept under the rug start coming up. And so, of course, even the numerical relativity errors also exist that we've swept under the rug. So now we have to clean the rug and get things at a higher precision and accuracy so that we don't have this problem that the models would disagree. And why it's more and more important, again, I'm crossing my fingers to still be important, please, is that the future of gravitational wave detectors is an even ground-based LIGO version, which means you're not building new vacuum tubes, you're keeping LIGOs in place and you're just improving the detectors themselves, sees this problem of now we're starting to have theoretical decision-making impact our ability to interpret these gravitational waves. And of course, if you build the next generation of ground-based, Europe Einstein Telescope, US Cosmic Explorer, and LISA, which is pretty far along now, a launch date of 2035 doesn't sound soon, but it is when it's a multi-billion-dollar project. And so that one is already pushing towards having the data analysis pipeline in place, which means you have the waveforms in place. And of course, we have the pulsar timing array out there. So this is just a really hard to read plot that shows you the pulsar timing array, frequency range, LISA's frequency range, and the ground base. So it covers a really big portion of the world. And these are artist renditions of all those things. So everything here means that we still have a job, numerical relativity. So let's get at it and produce better and better waveforms. The demand of these things, why is there a different demand? This is for mostly LISA. I do mostly work in LISA, so that's why it gets very LISA-centric here. I apologize. So the sources change a little bit, not from numerical relativist point of view. If you do vacuum GR, we don't care if it's 200 mass black holes or 2 million mass black holes. We just change the unit. But now we also get extreme mass ratio inspirals, which is not really in the purview of numerical relativity, but nonetheless is a very different source. We have a really big black hole and little ones falling in. And other things like galactic white dwarf binaries. The big thing is it increases the length of the signal and band. So here's an example. This is LISA. This is LIGO. This isn't even a big black hole. This is like a 1200 to 8 plus 80. This one's 3000 plus 1000. And it can be 4 years here before it merges outside the band. So the signals last longer. The supermassive black holes last even longer. And they have a very high signal to noise. Not these guys, but the massive black hole binaries, a few of them might have 1,000. So they're going to be really loud signals. And the problem with LISA and future gravitational wave Earth-based detectors, right now, it's like the early stage of making popcorn. You get a signal, right? This is going to be more like, when it goes crazy. So we'll have many signals happening at once. And so you have to have that nuance that you're not contaminating anything from errors in these signals. So that's why we have to be better, always better, bigger and better. So it's a challenge for data analysis. It's a challenge for the numerics. And I have a slide at the very end pinpointing some of the talks here this week are really going to help this. I'm really relying on a lot of people in this room to make the code. Yay, you guys, go, go, go. Because you need a really good code. So they didn't want to show your plot, Trevor. So what have we been up to, right? we're trying to figure out where are the places in our decision-making tree of numerical relativity that might cause the most errors, you know, how well we do truncation, just plain old finite differencing errors, how well we extract the waveform, which was bad for a while, gauge conditions we're choosing, but also that all sits here, also what parameters have we covered, because the models are reliant on where we are, and models tend to go beyond what we've done in numerical relativity, and then you have to be skeptical. And also other things that could be impacting, especially as we go to space, because now you might expect these black holes to be living in an active galactic nuclei, or something that could really change the way the signal looks, even though you have to put a lot of mass before you change that gravitational wave signal, but it could happen. And so people have been pushing this, one of them, Deborah, to understand where these errors, how they could impact our detection. So this plot is one of just looking at different numerical relativity resolution and seeing what would happen as you try to pick those out of the signal, and how if you didn't do all the higher harmonics, or if you had a large error, it could contaminate things downstream. So where are we right now? This is all coming from, Helvy's not here. Helvy, Helvy's in a PhD defense right now. So on the waveform white paper from Lisa that took us like 3 years to write, but it looked at all the NR groups, and it checked all the public catalogs for what parameter spaces we have currently covered. So Awesome put this table together for his paper coming out about where are we today. So this is the waveforms. This needs to be updated because SXX came out with a new catalog. Yeah. So what could you grab today? It's a lot of waveforms, but it's not millions, right? It's not complete coverage. You can see that we have a lot of equal mass cycle line spin. Of course, that's easy, but as you get to the harder and harder parameter space, of course, we have fewer and fewer of those waveforms. This is my favorite. Like sometimes we really don't, it's hard to do unequal mass, right? And this plot that Deborah did shows you sort of what it looks like if you grabbed a couple dimensions of that parameter space and try to see where we have holes in our understanding. This is the promised list of NR codes and the citations for the public catalogs associated with those codes. Some of these codes are in development. We put the asterisks when they were Einstein, probably because Helvy and I were involved, when there are Einstein toolkit based codes. So you can see how many codes really use Einstein toolkit's infrastructure. I think that's an important message to take away. And a lot of these codes aren't they're developing, they're not production stage, but you can see how many formulations are covered, which is great, how many are open source, and who's got some hydro and beyond GR. So hopefully it's a useful resource for the community. So what are we up to? Trying to figure out where people should spend their time as we wait for these fancy new codes to finish with Carpet X, et cetera, et cetera. So, you know, what's our goal is to have indistinguishability. So we want the waveform errors to be so small that we don't know they're there as far as the detectors are concerned. And so people have looked in 3G and in Lisa to figure out where those standings are. And then we've also looked at what happens if you push this through the full parameter infrastructure, like all the way to measuring the parameter biases. So let's see if I can get this plot right. Awesome can tell you if I don't get it right. So the problem here is that, yeah, I never get this plot right there. This is our total mass, and this is the gravitational wave cycles. Oh yeah, this is how many gravitational wave cycles you would potentially need. And you can see that it gets challenging. No one wants 1,000 cycles, you're crazy, is what you would need from Maya or an RIT. So basically, this is the Einstein toolkit line. This would be the spec code. And this is a bit of a lie in that you wouldn't want NR to do all that work. You'd want Post-Newtonian or self-force to do that work for you. But we have to figure out, that means we have to agree with each other. We have to overlap enough that the errors between us also don't contaminate everything. So that's part of the problem. And what else do we like to talk about? It was for mass ratio. So obviously the mass ratio makes this problem harder and harder. So the more unequal they are, the harder the problem becomes. And the fewer NR cycles we have on hand. So it's a really challenge. This plot's really pretty, but we'll skip it. So I'm heading for an early coffee break. Oh, I'm almost done. Oh, that's okay. So I was looking and very excited about what you guys are going to talk about, because not only will we get an introduction and an in-depth discussion of the Einstein toolkit. You see then, I would call these next two bullets, like how do we get the best waveforms out? So Deborah's going to talk about CCE, which is a way to really get a true scry waveform instead of what we do right now, which is a bit of a kludge. Huge in this week is going to be how you get faster and better numerics, which I've convinced you we need. And then the two big ticket items, I would say this is all in my head getting the best waveforms out. And then this is where we're headed, right? Let's go beyond GR. So Helvi will tell us about modified gravity efforts. And then everything I skipped matter, which is hugely important, especially if we can get a better detection at higher frequencies. Then we'd actually see the merger of neutron stars, and this would all be amazing. Not just for people who do astronomy, but for people who do fundamental physics and understanding the nuclear forces in a way you can't see anywhere else because you can't build a neutron star in a lab. So I think it's exciting time. I think it'd be a shame for the universe to fold right now. But anyway, we're just getting better and better in ground. Space is looking great. Everything's lined up. Things are going. The big space-based detectors are being built right now. I've seen the mirrors. They're really pretty. They look gold from the filters on them. The laser is itty. I couldn't believe a laser. It's very tiny. And so things are actually in preparation. So the detectors are getting better. This means we're going to get a bigger and bigger volume. So we'll have more and more events and increase the requirements on the waveforms. So we still have a pivotal role to play. Don't let anyone tell you that we're done. The models will take care of it. That's only if we were somehow perfect already. So, and I think the Einstein toolkit actually is underplaying its role in this. I think if we work together better, we would be more competitive with SXS. Right now, almost every model waveform out there uses SSX waveforms and not Einstein toolkit waveforms. And I think that if we could build a more cohesive language around our waveforms, that we could actually maybe take some of that space back from SSX. And so no matter if we do that or not, this is still a really exciting time to reveal gravity's role. So I hope the graduate students that are here learn all about ETK this week. Yeah, you can applaud. No, I'm kidding. I'm done. I'm done. Done. Question? It's been very quiet, like a class. No. You need coffee. I don't know if Carolyn has the coffee out there. Do I need to distract for another minute? Where is she? I told her I couldn't go to 10, but I promised 9:45. No questions? You're all excited? I should learn how to run Einstein toolkit again. Okay. I'm gonna be on Zoom like. Remember, Deborah used to try to get me to run on the cluster TAC, and I would forget to copy the waveforms over, and they would disappear. She finally gave up on me. There's like an age out problem. I don't know what's happening. So maybe I should sit in on that tutorial. Okay. All right. Well, then we'll hope the coffee is there, and I hope you guys have a good week. I'll be on Zoom with my puppy. She's too good. She tries to run. You all can really get up and talk now. All y'all. I think they have coffee out there.
I believe it's coffee break until 10:30.
Oh, sorry. Is that what I should have said? It's a coffee break until 10:30. Yay!
Yeah.